Okay, welcome everyone. I'm happy that you made it all here after lunch and afternoon snack, and we're really excited to talk about analytics with graphs, meaning graph algorithms and more. I'm Michael Hunger, Director of Developer Relations Engineering at Neo, and my colleague Amy.
Hello everybody, I'm Amy Hodler. I handle the analytics marketing for Neo4j.
Okay, Amy will begin and then I'll...
Yeah, so first, just to congratulate you all for coming to a session that I think is actually one of the most exciting topics in the study of graphs. Next few minutes, we're going to talk about two main topics. One is the study of real-world networks, and the other is graph algorithms and analytics, which is what you use to study those. Now, the reason why I think this is the most exciting area in the graph space is that it's all about understanding the world we live in and the networks that we live in and among. So when you think about what we're really trying to accomplish when we study these, it's understanding the complex behavior and dynamics of these holistic systems that are in the world. And those behaviors usually fall into about three different areas. One is, how do things spread through a network? The other is, how does something flow? What's the capacity for things to move through a network? And the other is, of course, what's the resiliency of the groups that I'm looking at? What's the influence on that? So if we take just a quick look at each one of those, if we think about propagation pathways, this is a very practical example of why you would want to study how something spreads. This is an example from 2010. It has to do with cascading failures. It's actually delay failures that were happening in the US airline industry in 2010. They actually had two really bad failures. The items in purple actually have significant delays. Greens are doing okay. If I had a time sequence, you would see the ripple from one coast to the other coast. But this is just a one example. This could very easily be an IT network. Cascading failures there. There's some examples using electrical grids, or this could be the spread of information. Let's say you want something to spread and to propagate. How best to get that pathway to do that? Another example, very practical again, is flow. So this kind of routing planning is used a lot to plan for things like least cost routing. Very common in the telecom industry. You need to get something from A to B, you have certain service levels to meet, but you have to do it in an efficient manner. But this could very well be how to get the flow of goods transported to your customer in the most efficient manner, or perhaps it's the most fastest manner. Maybe you're providing goods to an emergency service. So very different ways you could take a look at it. And the other area that is really interesting is group resiliency. Really fascinating area in general, because you're looking at how do groups possibly break apart, or how do you bring groups together? What's the stability of a group over time, and what are the influence points? This is actually from a really interesting study. This diagram is from a study of hierarchies in a Belgian telecom network. The items in red are French speakers, and the items in green are Dutch speakers. The first thing you notice is there's a lot of call volume going between each group within their group. And they saw this throughout their network, that there was an affinity by language, except for this one little cluster in the middle that's a bridge. That bridge cluster has communication mostly going in between the different groups, but not by language. So they didn't see a cluster by language within that node. So it's a really interesting bridge. And as we saw this morning, this might not be a telecom scenario. You could look at this from a fraud scenario, and maybe your middle bridge is a middleman. In this case, let's say we wanted to bring these two communities closer together. The way to disseminate information and try to gain more consensus would be to focus on that bridge. So group resiliency, a very fascinating area overall. So when we think about what graph algorithms can do to help us understand these complex behaviors, it's all about extracting structure so we can then model processes and make those really valuable predictions. And when you think about structure, what's interesting is in the real world, you don't really see much that's random. So it may feel like that some days, but in general, what we've seen and observed is that over time, there's this preferential attachment, which means if you're a node, you have a more likely chance to attach to a node that already has connections. And you might think of that as the good get better, the rich get richer, that kind of an experience. And what's really interesting about that is it really displays how entangled network structure and the evolution of networks are. And there's a lot of debate over why this is. Maybe it's some local heuristics, maybe there's some global cost estimation going in, but they really don't know yet. But what they do know is this is how networks grow, is there's a propensity in nature for things to have preferential treatment or preferential attachment. And what that leads to over time is very concentrated distributions. So it's a very lovely picture that shows a concentrated distribution in an online gaming network. And so here we've got over 380 sub-communities of this overall community. The top 5 sub-communities touch 50% of that community. So preferential attachment, more likely to end up with these hubs and spokes and grow in the influence of the hubs. And as you can imagine, if you kind of visualize that, what we're really looking at here is a power law distribution. And what that means is there's a lot of nodes with just a few connections and a few nodes with a lot of connections. We see this on the World Wide Web, we see this in business, we see this in nature. This is very common to see. And it is so common that a lot of network scientists believe that in nature you really don't see random networks. And when they think about random networks, what they're talking about is average distribution. Not a lot of humps, things are fairly flat, not a lot of structure. On average, things look like everything else. But what we really do see, so we don't see that in nature, but what we do see is, especially in social networks, is this very small world network behavior. So you have these clusters where things are very well connected inside your little network, your little friend network, and you're never too many hops away from somebody else. And you see this in like the 7 degrees of separation, or the old Kevin Bacon game, if you guys are familiar with that. Very common in social networks. And then the other thing that we see is also these scale-free networks. So you still get the hub and spoke, but what's interesting in a scale-free network is that you see the same hub and spoke structure over different scales, whether you're looking at 10 units or 10,000 or 100,000. That's really kind of fascinating, and the scale-free has an extremely strong power distribution to it. So this looks great. We've got some models. We know that the world kind of looks more scale-free and small world, but then what happens when we get the real data on our desk and we have to deal with this mess? So you can kind of look at this and go, well, I can see that there's structure, but I don't really know what to do with this. And there's a lot of research into how to unfold these messy, globby networks. And unfortunately, when presented with this, there's a real temptation to go with average, because that looked pretty messy. And on average, if I assume most of my customers kind of look alike and there's some similarities here in distribution, I can ignore the outliers, I'll just go with an average. But you really need to resist that temptation, because you can see here, mathematically, these are very different types of networks. And we know just from what we looked at that we're more likely to see small world or scale free. And on top of that, the structures are very different. You have flat versus hierarchy and topology. And I have a little video of what it looks like if you actually try to apply a random approach to a real network. And this is a network where we're trying to remove influence. You can either take a random approach and just kind of willy-nilly grab nodes and remove them, or you target the most influential. In this case, they use centrality to figure out what's the most influential nodes, then you go ahead and remove them. 19 clicks here, exceptionally different, totally different results. And you think about what this could mean if we were targeting, let's say, a disease network, and we needed to figure out what nodes we really need to take out. What's interesting is this approach is commonly used in that cascading failure example. So there was a European grid, electrical grid, where they were having trouble with some cascading outages and vulnerabilities. They looked at their network and they thought, well, we're having troubles with this. Maybe we should be more redundant. Exactly opposite result is what they ended up by looking at the centralities and where the influence was. They actually found with this kind of approach that if they removed just 4 nodes in their network, they reduced their vulnerabilities to cascading failures, because that was almost like propagating failure information. So pretty interesting, and it's not surprising that a model developed for connected data is taking off in our connected network world. And that's really what we're seeing now is graph analytics taking off. And you have to wonder, it's been a little while. This math has been around for a while. What's taking so long? And I think for the change is happening because we're really starting to see this critical mass of a few different things. First off, it's just big data. The ability to collect, analyze, affordable compute, affordable storage. We can really bring information together. Love big data. The other thing that's really interesting is this observation that there are these common structures. So those structures we were just looking at, the scale-free, the small world network, the recognition that there are structures that are common across domains, but there's also behaviors that are common across domains. So PageRank is a really interesting example because you see that used everywhere from biology to neuroscience to ranking pages to economic viability. So you can use these same methods, and fortunately the math is there. The mathematical tools are well known, they're established, they're tools that we can use today. The fourth thing that I think has really brought about some change is just this frustration, this unfulfilled promise of big data. We've collected all this stuff. We know there are nuggets out there, but the tools that are using this random approach that we had talked about, the approach of averages, haven't really revealed the information that we need to be valuable. So with that, I'm going to let Michael talk about how we move forward.
Yeah, thank you.
Thank you.
So the interesting bit about graph structures and graph data is actually that not only they capture information as attributes of your entity or attributes of your connections, but there's a lot of information hidden in the structure of the data. That's something that Emil showed in the morning, that the context is actually king, right? So I could look at all these individual elements as separate lone entities, but only by putting them into context, I actually can infer so much more wisdom about all these things. And graph analytics and graph algorithms help us using this structure to get more insight in our data. Usually what you can infer from graph algorithms are things like I get metrics about a graph, like what is the degree distribution of this graph, what's the size of this graph, what's the longest, shortest path, stuff like that. Something that's really interesting is what Amy mentioned in terms of relevance. So in the last few slides, so what are the influential nodes? What are the nodes that connect clusters? What are the entities that have within a cluster really high influence? And the next thing is, of course, how is this graph structured on a larger scale? So what kind of groupings or clusterings do I find in this graph, which might not be visible at a first glance, but for instance, by looking at weighted relationships between nodes, you suddenly can realize that, okay, not all relationships are created equal, but there are some that have a higher relevance and others that have a lower relevance, and by applying that, you kind of suddenly see these clusters emerge. And it all leads us to these structural insights. We won't talk too much about machine learning today, but there's a lots of really interesting bits and pieces that I'm looking forward to work on in the future with graphs and machine learning, from NLP to prediction of structure and data, to representing neural networks in the graph, being able to query neural networks, compare neural networks, and things like that. So that's just a teaser for where we want to go. And in general, it's really interesting, no matter if you look at, for instance, like Will does at political network of joint voting for bills, or if you have things like software architecture where you destructure a large system into smaller and smaller components, and perhaps you don't see the structure in your code, but actually if you kind of analyze the code, you see actually structures emerging by something like communication behavior, which entities in your system communicate with each other. The same is true for human organizations, where you see communication flows revealing structures in your organization which can be completely orthogonal to the actual organizational structure and which you should actually support. So there's a lot of stuff in there. One of my favorite examples for this is the Game of Thrones interaction network, because this made me actually realize that there's content or there's information that we know. So people that have read the books or seen the series kind of know stuff about this universe, but by just applying graph analytics and stupid algorithms who has no clue about Westeros can in the end infer the same information. So the algorithm can actually infer who are the important people, who connects other people, which clusters exist in this story network. And that was for me really kind of like an epiphany to see, even without knowing anything about the domain, such an algorithm can reveal a lot of insight about that. And that was quite interesting. How do you run this graph analytics processing? So far, there have been a number of options. There's Spark, there's Flink with Jelly, there's Graph like Giraffe, Gradoop as well. And so many things where you can take your data, put them into a graph processing system, run compute, and then take the results and move them somewhere else to continue to compute. This is definitely very valuable. It's also very scalable. You can use GPUs and so on. But what I always wanted to do is to simplify the process for the most common use cases, right? So this is kind of the petabyte use case when you have like tens or hundreds or thousands of billions of nodes in relationships. But what's about the common use case when my graph has like 100 million nodes, 1 billion nodes, 10 billion nodes or something like that? I really wanted to always simplify this approach. And that's where we are going to. So basically, we have an example from last year's GraphConnect. John Swain presented the network influence analytics on Twitter data, both for Brexit, but also for the US elections, which both turned out not to be that great, as you all know. But what it is, toolchain and workflow look like. So he had a really kind of complex toolchain. He pulled the data from Twitter, stored it in a message queue, put it into MongoDB, put it into Neo4j, extracted it out of Neo4j, put it in R, computed something, put it back into Neo4j, took it out of Neo4j again. So several iterations there, here, and then he put it into MySQL to visualize it in Tableau, or he exported it as GraphML to visualize it in Gephi. So it's a quite complex workflow, as you can see, right? And there were lots of moving parts, and there was a lot of data, lots of time spent in just data import, export, converting data from A to B, fixing conversion problems, and so on. So it was a quite tedious problem. And what we actually wanted to achieve is remove some of these moving parts. So for instance, we don't need to, for instance, store our tweets in Mongo. We can just store them in Neo4j in a proper graph structure. So that's one moving part gone. The other thing is that actually as a graph database, we should also be able to run graph algorithms ourselves. So there shouldn't be a need to export data from Neo4j to R to run something and write the data back and forth. But we actually wanted all to happen within the kind of graph model that's in Neo4j. And of course, if you want to visualize something in Tableau, you shouldn't need to put it in MySQL first. So there's a Tableau connector for Neo4j that you can use, and we can stream graph data directly to Gephi now as well. So there's also no need to export it as GraphML first. So we can kind of simplify the whole workflow into like 3-4 components, and I think that's much more manageable for someone. Also for getting started with the whole graph analytics problem. So for Neo4j, there's a number of tools and techniques that we can apply for graph querying, graph analytics. So one is, of course, Cypher as the lingua franca of graphs for creating and querying graphs, both in Neo4j but in a lot of other systems, as you saw today. My baby Epoch has grown also quite a lot and encompasses now a lot of data analytics tooling. And you can do a lot of compute and update with a single procedure call in Neo4j. We have the algorithms that I'll talk about in a minute. And we also are working on a lot of other analytics integrations with BI tools and other things as well, where we then can pull stuff easier together and don't have to go the extra mile. Okay, what are the algorithms that we're looking at that are currently available for Neo4j as efficiently implemented algorithms. So first of all, we have centrality algorithms, which capture things like pagering, between centrality, closeness centrality, degree centrality, and so on. So everything that kind of explores how important is a node, what's the relevance of a node, what's the influence of a node. Second one is clustering. That means a set of community detection algorithms like union find, Louvain, label propagation, and so on. Strongly connected components. And the last one is pathfinding, which is all about Dijkstra, so finding shortest paths, finding all shortest paths between a number of nodes, and single source shortest paths, and so on. So there's a wide range of algorithms already available, but as part of the work, we also build an infrastructure that makes it easier to add new algorithms as well. So from now on, we also have the ability to add new ways of doing graph analytics pretty quickly. So within a few days or a week, we can add new capabilities to this library as well. Basically, since last year, Cypher or Neo4j added the ability to write your own user-defined procedures and functions, which allow you to extend Cypher as a language. So whatever feature you are missing in Cypher, you can just build yourself as in any JVM language, deploy it to Neo4j, and then it's available as part of the language to be called with a single procedure call. And that was also the way how we wanted to expose these algorithms. So we didn't want to invent a new language or put a layer on top of Cypher. We just wanted to have an easy way of take your data, pass in a few parameters, select the algorithm, run it, and be done. So it shouldn't be more than like a few lines of code necessary to run even an advanced algorithm. So basically, we have two ways of doing that. So one way the algorithm works is that it streams results back to you. So imagine you run something like a centrality algorithm. It would return each node with the ID and the centrality score that it computed for the node. The problem there is from a certain size, it's hard to actually process the millions or hundreds of millions or billions of nodes that get thrown at you by the algorithm. And that's why we added a second way, which is able to take the results and write it back in a really efficient manner to Neo4j as properties on your node. So whatever is computed, you can specify a property name and it will be written back really efficiently to the graph. The other thing that I'm actually super excited about is projected graphs. So oftentimes the graph that we're working with doesn't have the structure that we want to run the algorithm on. So it could be a bipartite graph that we want to project into either direction. So for instance, I want to say, okay, I have, for instance, users that rated products. So I can project it into a product graph by the users that rated them, or I can project it into a user graph by the products they jointly rated, and then run actually the algorithm on this graph. And so what we did is you can just, instead of passing in something like a label relationship type into the algorithm, you can also just pass in two Cypher statements, one to create a node list and one to create an edge list or a relationship list. And then it will use the results of this projected graph to build up the necessary data structures to run the algorithm. And that's a super powerful approach because that allows you to apply any of your Cypher skills to filter, group, reduce, project the graph that you have to a higher granular graph to use for your algorithm. And that's actually available for all the algorithms. So this general syntax of calling these algorithms is consistent across all the algorithms. So if you ran one, then you can also should be able to run all the others. Okay. As I said already, for the centrality, we have pagering as a baseline algorithm between the centrality, closeness centrality, and degree centrality. For community detection, we have label propagation, union find. We have Louvain, strongly connected component. And we also added triangle counts, which are actually sitting between community detection and centralities, and also computing clustering coefficient. And for pathfinding algorithms, we have, as I said, single source shortest path, or node shortest path, and then also implementations for parallel Dijkstra, parallel breadth first search, and depth first search, if that's something that's useful for you. Okay, basically what we want to enable everyone to do is take your data, pull it together in one graph, run your compute, enrich the data, and then use this new information that you got from running the algorithms to improve the quality of your transactional queries, be it either for recommendations, be it for detecting certain things, be it for providing more information to decision makers and so on. And as Ryan showed in the beginning today, of course we can also use this information to provide a better visualization experience. So for instance, if you run a clustering algorithm, then we can use this information in the UI, in the visualization, to render really large complex graphs at higher level clusters, for instance, and then allow a drill down mechanism to go down. Or we can, for instance, highlight certain nodes with a especially high or low centrality as something that we want to look at. And because we added it to Cypher as user-defined procedures, you can call it from any API. So you can call it from Neo4j browser, you can call it from Cypher shell, you can call it from any programming language, from any driver. You can even integrate it with an object graph mapper like Spring.NET Neo4j by just adding these procedures to your repositories. So there's no limit in terms of which are the APIs that I can use this from, even from embedded as well. Okay, cool, demo time. So I will not be able to show all demos in full length because even as they are fast, some of these algorithms still run for a few minutes on large graphs. So bear with me and I will only be able to show some of them live and others only as a summary. So I want to quickly look at 4 graphs. So one is the Neo4j community graph. As you know, a developer community is very widespread and activity is happening everywhere on Twitter and GitHub, on Stack Overflow, on Meetup, and so on, and it's really hard to keep track. That's why we used our favorite graph database to keep track of all the activity of our community members, and that is one graph that I want to look at. DBpedia is a really quick example that I can also show live. The Yelp business graph is a really interesting, really rich data set that we only started to explore. There's so much more in there. And then Bitcoin as one of the larger graph examples, which is representative for typical money transfer graphs and similar things. Okay, the Neo4j community graph, as I mentioned, keeps all these users in continuously imported. So all the activity on Twitter, Stack Overflow, and so on. And so I just have a Neo4j desktop with my community graph here. And if I look, for instance, at users here, then I can see that I have a number of users. So the thing that I want to look at today is mostly the Twitter bit. So first of all, for running these graph algorithms, it's really useful to have something where you say, okay, I have a node which has a relationship to a similar type of node. So for instance, a user to a user, or a document to a document, or a product to a product, because that's what most of these algorithms are built for, kind of the typical math graphs. So what I want to start with, I want to take tweets and look at the retweet graph. So I have tweets which are retweeted by other tweets. So that's my kind of baseline graph. And I just want to quickly run PageRank on that. I run a stream method. So I get return back all the nodes and their score. And then I want to just output the tweets, their degree and the score. And I take a look at the top score. So this actually now took the data in the graph, ran the algorithm, computed it, and returned the scores from this. So you see it's pretty fast, and we see some tweets which are very generic, but which have a high degree, so have been retweeted quite a lot. But this also corresponds with the high PageRank score. So no big surprise here. The next thing I want to look at is actually a inferred graph. So we can look at users on Twitter by users posting tweets, and these tweets mention other users. So we can actually do an inferred graph. It's also called a mention graph, where I mention someone else as my connection to this other person, right? So and this is what we do here. So I have in this graph, I take this pattern of user post a tweet which mentions another user, and then I aggregate them by the two users, count how often that happened, and then just create a virtual relationship for Epoch to render this. And this is now my my inferred virtual graph where we have Neo4j here in the middle. You could also remove Neo4j, then you see that lots of the graph gets disconnected, right, like Amy showed before. And this is kind of my compute fabric or my compute model that I want to run these algorithms on. So it's kind of people having mentioned other people is my basic social graph model here. So, and now I can, for instance, run something like PageRank on this and can look at who are the most influential people on or accounts on the mention graph. So you see, of course, because it's the Neo4j community, Neo4j and GraphConnect are on top, but there are also some other people, like for instance Kirk on position 3, who's been very active in the database space and kind of publishing and tweeting a lot of things. So even if he's not a core member of the Neo4j community, his tweets got or he got mentioned so often that he gets a really high page rank. I'm there as well. Colin Emil is there, Adrian Coiler, the morning paper guy from Spring Source, and some others. Will is there as well. So people that have been mentioned more often than others, and especially transitively. So not just directly, but also transitively over multiple hops. And then I can take PageRank as well and write the results back. So I don't call the stream method here, but I call the procedure without stream. And if I run this, I actually get just a summary back that says, I looked at that many nodes, so 13,000 nodes, ran for 20 iterations. It took that many seconds or milliseconds to load the graph, compute it, and write it back. And now I have this PageRank property here on all my nodes and can use that to query my data again. And which I can do here, for instance, by saying, okay, I look at my Twitter users that have a PageRank property, take the top n, I skip Neo4j and GraphConnect because I don't want to see them, and then I actually continue to query, right? So I can take these top users and then say, okay, what tweets did they post, what text did they use, and then I actually create a virtual graph that says, what are the top tags used by my most influential users, for instance, right? And if I run this, then I see, so the, let's see, the red ones are the users, and the gray ones are these are the tags actually. So this is a user, these are the tags. So we can actually see what kind of activities did my top users exhibit in this case. And so on. So the other examples I'll show you here. On this a little bit larger machine. So here I have DBpedia, which is a dump of Wikipedia actually, which has in total 11 million nodes and 120 million relationships. So it's a smallish graph, but quite useful to run stuff on. So what you can do is, for instance, you can here again run PageRank on DBpedia, and if we do this, then we can see also really nicely. Actually, let me run this this variant of PageRank here. So it loads the data from Neo4j, computes the PageRank, writes the data back, runs 20 iteration on PageRank, touches the 120 million relationships 20 times because it's 20 iterations, and or actually it's more often because it does it per node. And if you look at it, so the machine gets utilized completely. So it has 144 CPUs, and all these CPUs are busy, and it took us a total 20 seconds to run PageRank. So get the data from Neo4j, run PageRank in memory, write the data back to Neo4j, was done in 20 seconds on DBpedia, which is quite nice. Okay, we can also run other things like clustering and so on. I can also here use these projected graphs. For instance, if I'm only interested, for instance, in pages in a certain category or pages with a certain tag or that cover a certain aspect, then I can also run sub-ranking algorithms. So for instance, I can also decide I want to cluster my graph first and then run, for instance, ranking on top of that. But to show you that not only large machines can run this, I actually ran this PageRank algorithm also on my Mac here, which has actually 2 CPUs, and I ran it with I think 4 gigs of RAM or so, And even here, compute it on DBpedia within 2 minutes and 30 seconds or something like that. So even if I don't have the monster machine available, even on my shitty Mac, it's still fast enough to compute PageRank on DBpedia in a reasonable time, which is pretty cool. Okay, the next graph. So you can also do clustering there, for instance, on DBpedia by saying, okay, what are the most occurring clusters, and then, for instance, use that to visualize the central nodes of each cluster in Neo4j. Yelp is a really interesting data set, has been used for, I think, almost 10 years now as also scientific data set and for competitions and so on. So it's business reviews by users where businesses have locations. And there's also users friend network in there, and we can project this user to business network, of course, into user to user business to business networks, and then we can run things on top of that. So this is just a basic computation on ratings, where we can do some statistical analysis, but we can also run something like a PageRank on the friends network in Yelp. And we can also run algorithms on these inferred networks. So I actually computed it. So the two users having jointly reviewed a business actually results in 1.3 billion paths in total. And if you flip it around by to businesses that have been jointly, where both businesses have been reviewed by the same user, it's 240 million paths. So that's kind of the data that you can run this on. And then you can, for instance, find clusters of similar businesses. You can find peer groups or people that have similar preferences for businesses and so on. So there's some really interesting stuff. And here what we created is actually we persisted a co-occurrence relationship for Las Vegas. So we kind of said, okay, all the businesses that have at least, I think, 5 reviews are now in Las Vegas and have been reviewed by the same people. I want to actually pull them together into a graph and then run algorithms on that, for instance, student find. So what's interesting is I actually don't get a lot of large clusters, just a single large cluster. So there seems to be a quite large overlap between all the businesses in Vegas. Could be because it's all, I don't know, on this trip, you know. And then you can also run PageRank on this projected business network. Where interestingly, businesses showed up which don't have a high ranking on Yelp, which led me actually to investigate the distribution of the ranking on Yelp, which is actually pretty bad because it's only between 3.8 and 5. So it's kind of, all the lower numbers are not available in reasonable amounts. So it's kind of interesting. The last example is Bitcoin. Bitcoin is a really nice payment network. So we got it from Greg Walker, who does Learn Me a Bitcoin and imports continuously all the data from Bitcoin into Neo4j. And it has 1.7 billion nodes, 2.7 billion relationships. It's about 600 gigabytes on disk. And we can use this network, for instance, to compute different things. So one was degree distribution, where I actually learned that people on Bitcoin don't reuse addresses. Right, so when you want to send data, money on Bitcoin, you always create new addresses, so you're not trackable. So that's something that I, for instance, didn't know. So first insight for me. And the second thing that we did was to look at what clusters or communities can we see in like this projected network from address to out to transaction to out to address. So it's kind of a 5-hop distance projected network, and then we take this network and project it to a virtual graph, run the algorithm on it, and then in like 300 seconds we get a clustering on top of these projected addresses in Bitcoin. So this was with 10 million, a subset of 10 million, because I didn't want to spend more time to wait for this. But of course you can also do it on the whole network as well. Okay. The design considerations for implementing this, we really wanted it to be efficient and fast, so we parallelized everything. So we parallelized the loading from Neo4j, the computation, and the writing back. So we can utilize all your CPUs. If you have a lot of CPUs, like on the new cloud instances, you get 128 CPUs, which are really cool. And we wanted to implement a higher level API that you can use to write graph algorithms against, which we call Graph API. And So far, my largest graph that I ran it on had 3 billion nodes and 20 billion relationships to compute things on top of that. So that's kind of what it does. It loads data from Neo4j in parallel, computes in parallel on top of the Graph API and writes it back. And as you have seen before, it keeps large CPU accounts really busy, which is something that warms my heart somehow, probably also the data center, but you know. And what was actually surprising for me is actually how well we did in comparison. For instance, if you compared with the GraphX paper on the Twitter 2010 data set for union find and for PageRank, we actually do not so badly compared to that. So that made me happy as well. And as I said, at scale, 3 billion nodes, 18 billion relationships on a large machine, computed in 1 hour 47 minutes, a PageRank on top of this graph, which was nice. Okay, so what do we want from you? We want actually your feedback. We want you to try this out, apply it to your own data, apply it to your own problems and questions, give us feedback, send us ideas, send us, especially also to Amy, what are the ideas that you have? How do you want to use that? Look at the information that we have. We have a channel on Slack where you can come back and ask us questions. There's the GitHub repository for the algorithms. There was a release just 2 days ago. It's quite easy to use and to install. And we also have a white paper that you can use for yourself, but also, of course, hand to your colleagues, to your bosses, and say, look, this is something that we can now do with Neo4j, and which is really cool. And as we all know, graphs are everywhere. And with that, I want to leave you and thank you for your attention and have a good day. Oh no, sorry, I forgot something. Sorry, my bad. Of course, all this work wouldn't have been possible with my amazing contributors. So I worked with a group of people who actually did all the work. So I just, gave feedback. And so Paul and Martin from Avantgarde Labs took the crunch of the implementation work, and Tomasz did an amazing job in documenting all of that. So I'm really grateful for this team to help me with building this. And with that, I want to close and thank you for your attention.